Okay, this is 2012 for response question. This is the last year of the old test format, and questions 4, 5, 6 you didn't get a calculator for. That's no longer true, but this is still a good problem. Okay, so what this says is at 298 K, that's room temperature, 25 degrees Celsius, and 1 atmosphere pressure, that's standard atmospheric pressure, the standard state of bromine is a liquid, whereas the standard state of iodine is a solid. The enthalpy changes for the formation of bromine gas and iodine gas from these elemental forms at 298 are given in the table above. A, explain why for the formation of I2 gas from I2 solid is larger. See how 62.44 is positive, which means it's endothermic, is larger than the enthalpy changes from Br2 gas to I2 gas. In your explanation, identify the type of particle interactions involved and a reason for the difference in the magnitude of those interactions. Okay, first thing that's very interesting about this problem is that there's actually two answers, and you only had to give one of them. There's two things going on here. The simplest thing that I think to understand is, we've probably done this diagram a lot. So what, you probably remember this, we have the three states of matter, and if you solid up here and gas up here, and then in the middle we put liquid. And we do this for a reason, because in science there's things going on here. When we go from a solid to a liquid, we call that melting. And or we talk about the melting point, or we call this the heat of fusion. Well, actually, let me do this first. And then when you go from liquid to solid, it's freezing. This is really a bad diagram. I apologize. And so what happens is, the heat of fusion is when something fuses, it freezes, but this number and this number are the same. It's just that this is an endothermic process. You have to put energy into a solid to get it to melt. And then this is an exothermic process, because this liquid has to give up some energy before it can fuse. And so the chemistry term for how much energy it takes is the heat of fusion. And then liquid to gas is what we call vaporization. And then gas to liquid is called condensation. I'm going to erase this, but I really like this diagram, because solid straight to gas, which is actually what's going on here, is sublimation. That's why we make this box a little smaller. And then gas to solid is called deposition. And one of the reasons I really like this diagram is that you can see that sublimation, melting, and vaporization are all endothermic processes, because the arrow's going up. You have to put heat into it. And condensation, freezing, and deposition are all exothermic processes, because the arrow's going down and it has to get rid of some energy for that to happen. Now remember, they took either answer, but I think I'm erasing that diagram, because I needed to do that background so you could understand the answer. They didn't expect to see that diagram in there. And again, they full credit for either answer. So I'll say first answer they would have taken is Br2 liquid to Br2 gas. If you look at this, this is a vaporization process. And then, but I2 solid goes to I2 gas is a sublimation process. And one of the things the diagram goes to show you is that the heat of sublimation is equal to the heat of fusion plus the heat of vaporization. Because if you think about it, let me just do it like this: solid, gas, liquid. Again, this is the heat of fusion. This is the heat of vaporization. Here is the heat of sublimation. You can see that this arrow plus this arrow would equal that arrow. So one of the answers they would take, which is probably not the answer that I would have given, is that obviously it takes more energy for sublimation than it does for vaporization. That's the first answer. I'm actually going to add a slide in here. This is just a totally blank page. However, one of the things I hope I've been hammering on, because it's hugely important, when they talk about melting point, freezing point, boiling point, heat of fusion. The reason I put the circle here is on the new test reform, everything's always at standard conditions. Heat of vaporization, heat of sublimation, vapor pressure of a liquid. I think that's it. There might be some other ones, but when a problem gives you information about this stuff, it is almost, it is not almost always, it is an intermolecular force idea. Um, it's an intermolecular force question, I should say. And so the interesting thing about this problem is you have to go into the AP test going, oh my gosh, let me go back. They're telling you enthalpy. This is heat of vaporization. This is heat of sublimation. Why? And so the question is, and this is why they took either answers, because actually both things are going on. This is vaporization, this is sublimation, but the answer that I probably would have given, because I've been conditioned to the idea that when they give you delta H and there's a phase change, that's the other thing. If you look at those diagrams, phase change problems are always intermolecular forces. Well, Br2 liquid, if you look on the periodic table, bromine is atomic number 35. That means it has 35 electrons whizzing around the nucleus at the speed of light, times 2, because it's Br2. I2, though, or sorry, this is solid. I is atomic number 53, so it has 53 electrons times 2 whizzing around the nucleus at the speed of light. So this is 70 electrons total, and this is 106 electrons total. And one of the things we've been talking about is that these are both nonpolar molecules because they only have pure covalent bonds. In order to have a polar covalent bond, you have to have two different molecules. But obviously, 106 electrons is what we call more polarizable. And all polar means is there's a region of positive charge and negative charge in the molecule. And that's just the random motion of electrons. There's going to be instances when there's more electrons on one side than the other. And so this sets up an instantaneous dipole. But the answer that I probably would have given, and remember, they would take either one, is that I2 solid has more electrons. Hope you can see that. That means, that implies it has greater London dispersion forces. Remember, those are the only forces that are at work between two nonpolar molecules. It has greater London dispersion forces, and because the molecules of I2 are more attracted to each other than the molecules of Br2 because of the greater forces. It takes more energy to cause the phase change. And so that they either took, it's actually a combination of both of these. They either took this idea that it takes more energy for sublimation than it does for vaporization, or the fact that you talked about I2 has more electrons, so it's more polarizable, it has greater London dispersion forces, and you have to put more energy in to cause the phase change. Which of the two processes has a greater change in entropy? So let me just say this again. You got bromine liquid changing to bromine gas, but then you have iodine solid changing to iodine gas. And one of the things when we learned about entropy, remember the definition of entropy is a measure of disorder. I would do something like this. Solids have the smallest amount of entropy because they're frozen. They can't flow past each other. And then you have liquid. And then I would do this double inequality because the gases are hugely the most disordered. But obviously, going from a solid to a gas is going to cause greater change in disorder than liquid to gas. So again, remember in the AP exam, answer the question first. I2S to I2 gas has the greatest change in entropy because, and then just talk about this. Solids have the least disorder than liquids, than gases, something like this. And so to go from a solid to a gas, sorry, probably should erase that so that you can read my writing. Causes, maybe not causes, results in more disorder than going from a liquid to a gas. All right, something like that. I encourage you on these essay questions, look and see what the scoring guidelines say, because I teach it a certain way and it's kind of interesting to see how the graders rate it up. I2 and Br2 can react to form the compound IBr, which would have the greatest molar enthalpy of vaporization. I2, so question here, I like this. IBr liquid, and then you have Br2 liquid. Okay, again, I think that they're, so what happens here is, and again, they took either answer. This is a non-polar molecule because obviously when bromine is connected to itself, there's no polar covalent bond. This, however, has a slight shift, and so this is a polar molecule. And again, they took either. Did you recognize that this was polar and this was non-polar? Obviously, polar molecules have greater intermolecular forces. Dipole-dipole molecular force is much stronger than just a London dispersion forces. But the other thing is because this is very slightly polar, because these are very close to each other, again, this guy has 53 electrons and bromine has 35, so that's 8, 8. This guy has 70 electrons. Again, even if you didn't recognize that this was polar and this was non-polar, this has more London dispersion forces than this. And again, they took either answer. So remember, always answer the question, which has the greater molar enthalpy of vaporization? Again, molar enthalpy is H. Molar just means kilojoules per mole. And vaporization means it's going from a liquid to a gas. And remember, this is a phase change, and phase changes are always about intermolecular forces. They would take either answer. So answer 1, IBR is slightly polar. We don't even know that, because remember, it has to be greater than 0.3. But if you say that and you think it's polar, then they understand that you understand London dispersion forces, and BR2 is nonpolar. Dipole forces are stronger than London dispersion forces. So IBR, you don't have to put the bond in there, IBR has a greater molar heat of vaporization. To tell you the truth, I'm not even all that sure that this is a polar molecule, because I didn't look up the electronegativities. And so I actually, again, prefer the second answer better, which is the same as question 1. Same difference. Start with this. Start by answering the question, which is BR has a greater molar heat of vaporization. Actually, this should probably be the first sentence. And then after that topic sentence where you answer the question, then explain it. So again, second answer, IBR has a greater, notice I missed the ER up here, molar heat of vaporization. Again, here is the notation, H not vape. And the reason, and I'm not sure, because remember, to have a polar molecule, you have to have a polar covalent bond, which means the electronegativity difference has to be greater than 0.3. And I know their difference, but I don't know if it's greater than 0.3. So I would say something like IBR has more electrons, so it is more polarizable, and that just means the probability goes up that there's more electrons on one side than the other. It has greater London dispersion forces, named after Fritz London, so it's kind of like a title, so like we capitalize it. So it takes more energy to cause the phase change. Again, no calculator. These are essay questions. And again, on the AP exam, they can be answered in 1 or 2 sentences. In the first sentence, you should answer the question. All right, next thing, an experiment is performed to compare the solubilities of I2 solid in different solvents, water and hexane. A student adds 2 milliliters of water and 2 milliliters of hexane to a test tube. Because H2O and CH4 are immiscible, 2 layers are observed in the test tube. Okay, this is code. Immiscible means you're trying to mix a polar liquid with a non-polar. Oil and water don't mix. Water is highly polar because it contains dipole-dipole forces that are especially strong because it contains hydrogen bonds. And so you have a polar liquid and a non-polar liquid together, and they don't mix. Um, and then a student drops a small purple crystal of I2, which is nonpolar because there's no polar covalent bonds. The CS4 layer becomes light purple while the H2O layer remains virtually colorless. So the question is, how come iodine dissolves in the solvent hexane but not water? Explain why the hexane layer is light purple while the water is virtually colorless. Your explanation should reference the relative strengths of the interactions between, nice pause or space there, and the reason for this difference. And so basically, there's a thing, you don't have to have this in your answer, but like dissolves like. So in other words, um, polar or ionic, because ions have charges, um, polar or ionic compounds will dissolve in polar solvents. Nonpolar compounds dissolve in nonpolar solvents. And so that's what like dissolves like mean. You don't have to put that in there, but you need to say something like, well, I would say that, let me just say this, H2O, this is just background for you, it is polar, hugely polar. It has dipole forces that are particularly strong hydrogen bonds. Remember, hydrogen bonding is when hydrogen connects directly to oxygen, nitrogen, and fluorine. It has polar, especially especially strong dipole forces called hydrogen bonds. Whereas C6H14, because it has symmetry, is nonpolar. And then I2 is nonpolar. And so the question is, when you put these together, you get two layers, they're clear, and then when you put the iodine dissolves in this one, but not this one. Dissolves in the hexane, but not the water. And then we're supposed to say why. What is going on here? Why is the difference that it's soluble in one and not the other? And so I'm going to roll down, I'm going to switch colors, and then we're going to say something like I2 cannot dissolve in water because it would need to disrupt the hydrogen bonds. Now think about that. I just want to draw a picture up here. What, we talked about, like, why can water bugs more dense than water walk across the surface of water? It's because the positive side of one water molecule, so hydrogen, oxygen, is attracted to the negative side of another water molecule. And these are like little tiny baby magnets. And they're really attracted to each other. And here comes I2. Well, this is a partially negative charge. This side is a partially positive charge. These are highly attracted to each other. It's not attracted to I2 because I2 doesn't have a charge. And so it's not going to break apart and let the I2 in here, because that's basically all dissolving is that, for instance, when you put sodium chloride in water, it dissociates into sodium and chlorine, and the sodium molecules are surrounded in all sides by the negative side of the water molecule, and then the chloride ions are surrounded by the positive side, and they become evenly dispersed, and that's what dissolving is. But you can't disrupt this. So then, just to be sure, that just doesn't happen. Okay, but then they want to know more. And so then you would say something like, I would say something like, let me grab this pen, sorry. I2 and C6H14 liquid only have London dispersion forces. caused by the random motion of electrons. So it is easier to disrupt, it is easier for the I2 to dissolve. And meaning the intermolecular forces. I think that's enough. Again, these essay questions are even hard for me. Like, make sure that you say it succinctly and that you give them enough information. Again, highly encourage you to look at the scoring guidelines. All right, next page. A student adds a small crystal of Ki to the test tube. The test tube cork is inverted several times. The I negative ion, so basically it's saying that Ki, when it hits the water, it dissociates into potassium ions and iodide ions. And then the iodine ion hooks up with an iodine molecule and it makes I3. Draw the Lewis electron dot structure for I3. I didn't draw the box, but here's how we would start. I. You don't have any hydrogen, beryllium, or boron. This guy has 2, it wants 8. This guy has 4, it wants 8. This guy has 2, it wants 8. I count 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. ORP is 20. But then when I do VE, I get 7 plus 7 plus 7. And then this minus sign means there's an extra electron. And 7 times 3 is 21, and 21 plus 1 is 22. And so what happens is ORP is less than VE, and that means the central octet expands. It gets bigger. It's an octet rule expansion. And so the picture would be, this is what should be in your box. This guy has 8. This guy has 8. But this guy has 10. And then we got to do this in the box because it's an ion. And this ends up being, now they did not ask you for this for the question, but it's going to come up in the next question. This is an A, B2, E3. And remember, 2 plus 3 is 5. And so this kind of looks like, here's the North Pole, here's the South Pole, here's the equator. So I got 3 of these evenly spaced. 1, 2, 3, 4, 5. But now empty, empty, empty. These are gone because of VSEPR, valence shell electron pair repulsion theories. Anyways, this shape is linear. And so this, not that that matters, but that's just a shape. In which layer would the water hexane be the higher? And I'm going to answer the question, in the water layer. Why? Well, because water is a dipole. It has a positive side and a negative side. And this is not a molecule. It's an ion. It's a charged particle. And so what happens is Y, I3 minus has a charge. It has a negative charge. So it would be attracted to the positive side of the water molecule. Oops, got an extra E there. This, I don't know how you need to put this, but this is called an ion dipole force. It's not an intermolecular force. Intermolecular forces only occur between molecules, not ions. This is a huge concept when we're doing solutions. That's the reason why ionic compounds tend to be soluble in water, like sodium chloride. All right, that's enough.